Hi, my name is David Capwell. I'm a software engineer at Apple and a committer to the Apache Cassandra project. Today, I'll be talking to you about property and fuzz testing in the Apache Cassandra.
Is your mic on?
Supposed to be. Can you hear me?
Yeah.
All right, this needs to be closer to me. How about now? Can you hear me now?
Yes.
Good. All right, so today we'll be talking about a couple of things. One, why should you care about this idea? What does property test look like? And how can you evolve it in different ways? So first, why should you care? We're all developers. We've been writing code for a long time, and we all know that we know every edge case we're working on. We know how it's integrating with every other system that we're working on. And your change is very simple. It is very safe. We can push it to production on a Friday at 5 p.m. There's nothing to worry about. Wait, no one has ever said this before. Okay, so let's start looking at like a very simple test. In the Apache Cassandra, you know it's a database. We're going to create a table. We're going to insert some data into it. We're going to read it back and verify that it has the data we wrote. It's a very simple test. And then we realize, well, Cassandra has different shapes of a table. We have clustering keys. We can test that. So let's have another test of clustering keys. And then we remember clustering can be ordered. So we need yet another test of keys. So we do that. So far, we're great developers, and we're realizing we've only tested one type. How about let's add one more? Great. We've added all the edge case, the cases you care about. Everything should be working. It's working. It's working. Let's try some more. So UDTs have been an issue for this project for a long time. So we're good developers, and we created tests for UDTs, and it's still working. Don't know why this guy keeps on complaining. But then we realized all of our tests so far have been using bind variables. So the language supports literals. So we're going to be good people and do literals. And it crashes and runs. Why is this? Well, in Cassandra, when we have a reverse clustering key, we have a hidden type called a reverse type. And you have to remember in many, many, many parts of the code base to unwrap it. And we forgot to do it here. So that's a simple bug. That's the one edge case. There are not more. There are not scarier ones. Please go to the next slide. Math is hard, right? So does anyone know what is negative 42 plus negative 42? Apparently no one. Everyone's on the same level as Cassandra. Negative 84. So we write some data into Cassandra, and we read it back, and the Cassandra can't find negative 84 either. And why is that? Again, it's hard. We are using variable ints. And with the variable int, negative 84, it is 1 byte. But Cassandra used the wrong type. It actually used integer math. So it wrote 4 bytes as negative 34. So you query for 1 byte. You don't find it because you wrote 4 bytes. 1 is not equal to 4. We fail. Let's have some more fun with that. So we have 2 large numbers. We multiply them together. And Cassandra then corrupts the database. Great. This works in every we just chose the wrong type yet again. We did int math, we did int overflowing, and we chose the wrong thing. So what can we do? And how can we make things better? We have to acknowledge that we don't know all the edge cases. We don't know how it's going to be interacting with all the data systems. But maybe we can generate these things. So how do we do that? And that's where property testing comes into play. So what is a property test? What does it look like? There's a couple of basic things, and I'll go over each one in isolation. So first, you have to start with a source of randomness. And the most basic one is, give me a number between some range. Once you have that, you have to define your property. Here I'm saying my property is the numbers between 0 and 100 divided by itself equals to 1. And wait, there's that insert. A property is just an insert that you've been doing your entire career. You've been writing property testing, did not know it. We're fancy people, so we like to rename things. So yeah, these are property tests, these are normal tests, these are assertion tests. They're whatever you want to call them. But it's just as an assertion. It's something you've already been doing. And we run this test, and it's passing. There are no bugs. Everything is awesome. And then you think about it for a minute, and you realize 0 divided by 0 is not 1. So why did this test fail? Well, you were getting values from a range from 0 to 100. There's about 100 elements in it. So in a perfect world, you must run this test about 100 times to see the failure. So you commit this code, go on vacation, come back third of a year later and you find out it's broken and you need to remember how any of this works. So you realize with these kind of tests, maybe we should run them multiple times. So we run them in a loop. So we run the test again 1,000 times, and now it fails very frequently. Now, when you're dealing with a real test in CI, you're going to get an exception, and you don't know what the input is, you don't have to reproduce it. So you need some way of taking these tests and making them reproducible. So in most random sources, we have a concept of a seed, and that has the property is with the same seed, if you call things the same way, you get a deterministic behavior, everything is consistent. So if it fails in CI with seed 42, it will fail the same way on your laptop with that same seed. So we control the seed, and if it fails, we throw it with the same seed, and we get such information. Great. Now you might be thinking, I have complicated things, I have all these types I have to deal with, I don't know how to do all this with integers, and that's where we have this concept of generators, or gens for short. So given a random source, return some data. So we have here random UUID, which is create 2 different logs, do some math on them to make sure it's compliant with the spec, and then return it. Or 9net address is 4 random bytes, so you just generate 4 random bytes. Or status, well, you're selecting from an array, from an enum, so you just select an offset. But maybe your type is more complicated than that, right? And that's where composability comes in. So here's an example of key space metadata, where it's based off the name, the kind, the parameters, so forth and so forth. So what you do is you have a name generator, a kind generator, a params generator, and so on. These types compose. So how, you might be worried right now that that's a lot of work to do. I don't got time for that. I need to ship something on Friday at 5 p.m. But really, most of these things already exist in the Apache Cassandra project already. We have hundreds of non-Cassandra generators that you can leverage. Do you need to work with DNS? Do you need to work with time? We probably have what you're looking for. And when you're testing Cassandra itself, we have a lot of Cassandra-specific things. Are you dealing with our type system? Are you dealing with different tables? Do you need to generate data for the random type that you're seeing? Again, we have all those things covered already. So how do we bring this together? So you could either hand roll, like we saw before, with all of the copy paste we have, where you're controlling everything yourself, or you could just call the existing functions we have. So we have the Qt function, which returns a builder. You'll see one in a minute. You then say for all, in this scenario, for all integers, and we do the test we had before. Value divided by self equals 1, and when you run it, you get a very similar error message. You see the seed, how many examples, the error, but you also see the values that are put into the test, and you can then rerun it. So let's take that seed, put it into the builder with seed, and you can now run any debugger and reproduce that same test with ease. So how do we use this in the project? So here's a simple test from iPartitioner test. So this is saying take any token that could ever exist within the Cassandra database, convert the token into a comparable bytes. This is a feature we have for our tables. Read it back from comparable bytes back to the original token and make sure it is equal. This is a serialization deserialization test. We have this pattern a lot in Cassandra, but we don't have this pattern of test all the time in Cassandra, so we can do better. And so we have the messaging. We have another one for iVersion serializer.testSurvey. It's such a common pattern that we have already existing function for that. So you just pass in your value in your serializer, and it will rerun that serialization test for you. One thing to note with these types of tests is that I'm saying here for all tokens, whenever we're at a new partitioner into the database itself, these tests now grow as they start including the partitioner that they're running against. So these are not a static snapshot of one point in time where we're testing murmur in isolation or we're testing bytes comparable in isolation. We're always testing whatever the database has, and as we add more, the tests grow and expand with the cluster. So let's look at the test we had before. Right? We create the table, we insert, and we read. So how do we turn that into a property? So we have a couple of usable functions. If you look at SQL tester, we have the create key space function, which creates a randomized key space. So it's going to play with key space parameters. It's going to play with different partitioners. Then we're going to do create table, which is going to create different shapes of different tables with different parameters inside of it. Then we have create mutation. This is using a new AST that we wrote for testing. So we have an AST of the CQL language, so that test can generate a valid CQL, manipulate them, and compose them in different ways. So we can now create a valid mutation for that table, and we insert it. We then do a select on the primary key that we did for the mutation, read it back, and we verify that the rows are mutation defined. If it's an insert or update, the rows are whatever we wrote. If it's delete, the rows would be empty because we deleted it, there should be nothing. So this test here found all the bugs I reported before. So it found all of the arithmetic issues that we had. It's found issues with UDTs, it found issues with vectors. This has been finding a lot of issues, so it's been hard to merge because they have to fix those things. But now you might think to yourself, I have something more complicated than a simple property. I have all this data that I have to manage. So how do I do something that has all this complexity? Well, that's probably where stateful properties come into play. So what is a stateful property? It's just a property that has state. If you say anything backwards, it sounds smarter than it is. Typically, these tests come with a form of a model. And you hear model, and you're thinking you're modeling the entire depth of the universe. There's all these different edge cases that you have to worry about. And again, I don't have time for that. But one thing to note is that models follow the 80-20. Is with a very stupid simple model, you cover 80% of all edge cases, and you can just start from there. So let's take a look. So I work on the Accord project within Apache Cassandra, and in there we have to deal with a lot of ranges because we are tracking how all the different transactions are modified over different ranges and what's being updated. So we have a lot of mutations that are constantly happening. And the interval tree in Cassandra was too inefficient because we're rebuilding all the time. So we built a new range tree to make it more efficient. So I created a new data structure. I should test that data structure, right? So I have a stateful test. And I need to figure out how do I test this thing. A range tree is a search tree that offers the ability to store ranges to values. I can find a whole bunch of values that intersect. That's complicated. We can simplify it. So let's remove the search. So it's just a map of range to a list of values. That's still too complicated. We can simplify it. It's a map of range to value. It's a map. It's a map. My model is a map. So here I have a normal tree map that's just range to value, and then I have the range tree, and I'm manipulating it to make it look like a map as I can. And then I need to figure out what can I do during that. I can do create, I can do read, update, and delete. You've probably heard of this before. So I'm going to select one of those actions to perform, and then I will do that action. So what do they look like? So for create, you need to look at the model and see what does not exist. Find a key that does not exist, add it to the model, add it to the tree. And for read, it's the opposite of that. You have to read from the model, read from the tree, make sure that they produce the same value. Cool. We have the same test in SAI as well. So if you're not familiar with SAI, it's a new indexing system in Cassandra 5.0. And we have this test that is going to create an index on one of the values. And a secondary index is just a value to a list of partitions or rows in SAI. So that's what our model is. It's a map of value to a list of values. So we insert 1,000 partitions. So we know the partition that we're writing to. We know the term. We just update the map. And we then read back from Cassandra. Does Cassandra match on? Now, when you're dealing with state, you might have to start worrying about biases. So what is that? What does that matter? So many times when you have different types, they have very large domains. If your test works with 1 and 2, it might not work with -1 or 0 or min-max values. Or maybe your type has some relationships that you might not realize about. Modify for each other. Or maybe there's an edge case that you really want to hyper focus on. So you might want to inject a bias into this to cover these cases. So let's look at how we can do that. Go back to the range tree example. When the tree is very small, it is basically a list. So you want to make sure that it grows enough so it can split, and then you can find the correct split, search that split. So it's important that we bias towards the splitting function. Can you do that? Well, we take this test from before, and we see that we're looking at the actions that we can perform: create, read, update, and delete, and we're randomly selecting it. And by default, randomization is uniform. So that means create and delete have equal probability. So we'll create something in the test, we'll delete it, we'll create it, delete it, create it, delete it. This test is typically pretty small, and we never actually hit grow. So we might want to change the distribution in which we're selecting. So there we call the all mixed distribution function, and this returns a generator of generator of action. That sounds confusing, but the top level generator is selecting the distribution you want to select. And at the start of the test, we do action generator.next to select the distribution. So we always select the distribution we're selecting for our test, and then we call the test the same way. So the first time we run, maybe it's uniform and it's like we had before. Maybe the next time it's a zip band distribution. So create is twice as likely as read, twice as likely as update or delete. Or maybe it's a random distribution that we just formed on the fly unique to that iteration. Great. Now let's look at types. So we have the INET type in Cassandra. And INET can represent IPv4 and IPv6. IPv4 has this property that you can convert it to IPv6 and back again. So there's some form of equality there, even though they're physically not equal. So let's test that. So here I'm going to create a list of unique IPv4 addresses, and then I'm going to copy that list and map it into IPv6. So I have a unique list of IPv4 and a unique list of IPv4 and IPv6. And I run that SAI test that I showed you before to show it. And you would imagine everything would just work just fine, right? Because IPv4 and IPv6, they're two different byte values. So this test should be working just fine. But this test actually ends up failing with SAI. And that's because in SAI, it made a simplification. So rather than having an index that has to deal with IPv4 and IPv6, then they're two different sizes, and now we have variable lengths. It made the decision all IPv4 addresses become IPv6. So if a user writes IPv4 and IPv6, and you start querying, you can start getting rows that you're not expecting because you wrote IPv4, but you queried for IPv6 or vice versa. So there is a mailing list thread about this topic from a while ago that Caleb sent out. But like I showed before, is that if you want to write these kind of tests, we already have a lot of existing functions for you. And in the project, we have a stateful function as well. It's very similar to the Qt function. It's a builder. But there's a big difference in the check function. Rather than a lambda showing the lambda input, you now have something called commands, where a command has to deal with a state and the system under test. So if you think back to the range tree example I had before, the state is the map, and the system under test is the range tree. So you define how to create both, and then you have to define what can you do in your test. So here we have a whole bunch of commands we can define. We have create, we have read, which is not based off anything present in the model, it's just a random read. You've got key read, range read, you've got iteration, create, you have conditional operations, so I can conditionally make sure that if the data is present, then I can do a read on something that exists, or I can start doing deletes. So what does a command look like? So here's the example from range command. You have two methods, the apply method and the run method. The apply method works on the state. So in the range tree, it's the map. And since we're doing a range search, maps don't do that. So you end up doing a linear walk over everything to find all your results. And in the run method, you do it over the range tree itself or the system under test. So we can do a search there. You have a check post conditions that let you verify that the outputs match what you expect. In this case, that they're both equal. And you have a detailed function for heritability. So when we run this test, we get a failure. Right? We're using it for development to help find these issues. So here we get a similar error that we've seen before. We get the seed, examples, errors, but now we get something new. We have the steps. As you saw with the test before, we're having multiple different iterations for each stateful step. That's just called step. But we also have something called history. And history is the human readable list of every single step that we took. So you can debug how this happened. So we did a create of the range, we did token read, we deleted everything, we did another create, and we did a range read that intersected that range, and we expected 5, but we did not get back 5. We found a bug. So now we can just rerun the test with that seed, debug everything in isolation, and figure out. Cool. So now we can get a little bit more fancy and start talking about simulation. So simulation testing is just simulating one or more systems for your test. Maybe that's thread scheduling, maybe that's messaging, maybe that's gossip, maybe that's whatever you want. You're just simulating one specific thing. And you can simulate as much or as little as you actually want. Do you need to simulate all of Cassandra in a distributed cluster with all the locking and make sure it's deterministic? Well, we have the simulator. It can basically do anything you throw. Maybe you're working on a protocol and you want to make sure that the networking is correct and then you can handle failures. Well, we have messaging stuff. Or maybe you want to make sure that when you're scheduling that you don't have any race conditions. So we can do things at the thread level. We have things for different levels depending on what you're looking for. So let's look at a test that we have in repair. This is called the happy path test. It's the happy path test because it's a happy path. There are no failures. Nothing should ever go wrong. If this ever fails, you fundamentally broke repair. It should never be failing. So how did this test work? Is we create a cluster. And this is not a real cluster. This is a mock cluster that is fully simulated. And I'll show you that in a minute. We then do 100 repairs. And we create the repair. We start enqueuing all the work to happen. And then you see at the bottom cluster.process all. This is the thing that actually does all the simulation. We'll do all the messaging, all the threading, and make sure everything runs, and then everything finishes. Once it finishes, repair is successful, and we can verify that. So how do we do this? Well, when we added simulator to the project, we made it so that the low-level integration points became interfaces. When you're dealing with threads, you now have executor factory. When you're dealing with time, you have when you want to deal with messaging, you now have message delivery. These are all interfaces that we can implement and simulate in different ways and add chaos into the system. So looking at the cluster from before, we have simulated executor factory. Like I said, this is the thing that deals with all the threading. What this does is it puts all the tasks from your executor service into a priority queue. And it defines the priority based off of time, which is something we are simulating. And the progress of time is actually the progress of work, not real time. So then the test is able to span hours, weeks, and days over a period of seconds in the room. We then select random partitioners, random number of tokens, and different schemas for the cluster. And then we give each node the ability to do messaging. So we can get messaging. So there we have simulated message delivery, and that's able to mock messaging between all the different nodes and talk with each other and have chaos. Okay. So when you're dealing with simulation, you might want to be checking if you can handle different kinds of faults. So what are those faults that you can do? Well, with scheduling, you can start playing around with different delays. Sometimes you have really large delays, sometimes you have really short delays. Or maybe you want to change around order. You enqueue A and B, and then you want to execute in B and A in one test and A and B in another. And with messaging, you're probably all familiar. You can have partitioning, you can have one-way partitioning, you can have bi-way partitioning, you can have message drops, Cassandra loves to drop messaging. You can have delayed messages, and so forth and so forth. For each of the different integrations, for each of the different interfaces, you have different forms of faults that you can add into the system to expand your tests. So we go back to the happy path test and repair. We can make a slight change, and we can add enable message faults. So this will make it so all possible messaging faults are enabled into this cluster, and repair is going to be running a whole bunch of messaging faults. And for anyone who's used repair or Cassandra for any length of time, you are thinking that this test should be burning in fire and not working, and you have exert settings. It's exert success. So in either 4.1 or 5.0, I don't remember, I it so that repair can do retry messaging, and I have item potency for every single message all the way to IR. And this test was critical to proving the correctness of that implementation. Since it's testing all message reorderings, retrying of messaging, a whole bunch of just in-flight things that come in the line time, does repair handle it properly? And this test is able to run 1,000 repairs in 30 seconds. So I can make sure that it's working on a whole bunch of edge cases. But you don't have to stop right there. So you can simulate repair itself. Repair is a multi-step protocol. It has preparation, it has validation, it has streaming. So you can inject your own faults at those layers itself. So we take a variant of this test. So we enable message faults, we run the repair, and we get all the participants for that repair. We select one of the participants and we're going to inject it. Maybe during the prepare phase, we're going to say that there's too many compactions backed up, we have to fix the repair. Maybe it's during validation and we corrupt IR or we corrupt the disk. And we're making sure that one, repair actually terminates. This has been a long-going issue with repair. We now make sure repair actually terminates and does not leak resources. And two, that when it fails in a way that actually makes sense to an operator. So the assert on the failed is a little bit more complicated because it has to make sure all the different kinds of errors are human readable, but you don't have to worry about it. So, in closing, there's a couple of things I want you to take. One, when you're working on property testing and you want to add that into yourself, is you have to realize you're not starting from scratch. There's a lot that you can leverage today to get going. Also, most tests that you write today or that exist today can be converted to a property test. And it shouldn't be too scary to either migrate or write in accordance. Another thing is your tests grow with the database itself. As we add new features, as we add new capabilities, the existing tests now start to include those new stuff. You add a new type, all the type tests get included to include that type. You add new partitioners, we do the same. As we add more of these type of tests, it grows with the database and it makes it so we have more confidence in new changes. And when you hear the word model, don't be scared. They follow the 80-20 rule. Start stupid, it's going to get you all the way. Right? With that, any questions?
Question on failing seeds for tests. I've seen in past slides, they suggest actually taking that failing seed and duplicating the test and committing it with the failing seed to prevent regression very quickly, because you know, like you may have run these tests, 1,000 times before you find some esoteric failure. Do we recommend doing that? Is that something that we should do?
I would recommend against that. I agree in principle that failing case, we should have a test covering the failing case. And why I recommend not doing that is something that people learn early on when they're developing their code, is that you make one small change and the random history no longer lines up. You choose to take the left path rather than the right path, and then every decision from then on is completely different. It's the butterfly effect in principle. So rather than committing with that failing seed, you will never know that you took a different path. So it would be better to recreate that test, showing that that failure never regresses. If that makes sense?
Yeah.
Jordan?
Kind of transitions nicely to my question. Out of, besides the folks I work with at Apache, probably the person that does the most of this kind of testing. And I know with quick theories, things, my question basically is around shrinking, is that we largely just kind of like screw shrinking. To the point of like those branch paths and the randomness, et cetera. Do you think there's a world where like an effort to make shrinking viable would be beneficial, or do you just think it's a total waste?
We disabled it years ago, and I've never cared.
Okay.
So it would be nice to have the minimum failing case. But a recent thing I've been doing is there is a test on Trump now called the topology mix-up test. And it's going to do random topology changes, random cluster operations, SQL operations, and they're all racing with each other, and pure chaos. And shrinking that is annoying as heck. But with the history function in the stateful builder, it's you as a human can easily like eyeball what's important, and you can manually shrink yourself. And whenever you're dealing with neural property, there's a feature in the Qt function that we have in the Cassandra project, not the Quick Theories project, where there's a concept of purity. So whenever you fail, you actually get the seed for that individual failure and not for the beginning. So you can just immediately hit the existing issue in the debugger. So in practice, I've never really needed shrinking. It would be nice to have, but it hasn't really been an issue.
Do you
So,
get histories that are like crazy long, or do you find those histories? Or, I mean, I guess your point was, even in a big history, do you find it easy to find?
so the question on do I find issues with small histories? Well, when you start testing something for the first time, things blow apart. So right now we have the issue of small histories find a lot of issues, and then you fix them, you stabilize them, and then they become more stable. So they need to go to longer histories. So we're not at the longer histories phase yet. I know Alex has done a ton of work with Harry, which does a lot longer histories since it's designed for days and weeks. And some features work great, and you just can run over a long period of time, and then maybe after a couple of days you find issues. Most issues fail right away. Like when Alex worked on adding group by support into Harry, it took 5 seconds to crash. So most issues have that short history thing. You don't need a lot of complexity. You just need to remember, I did not think to restart a node, or I didn't think to put 4 there or null there. So I think we're at the early stage right now. Okay.
This problem of edge cases is not unique to Cassandra, but for example, in Cassandra and the latest we found these edge cases. So, can you recommend like a way to abstract this code and reuse it in other projects? How easy would it be to do that?
So the question was, the problem is not Cassandra specific. I have that problem in this other code base. Can I leverage that? And in short, it's not too hard. Alex and I talked about how we have a lot of testing infrastructure, and 99% of it doesn't know about Cassandra's existence. It's only that 1%. So making it its own standalone library so you can use it in other contexts wouldn't be too hard. It's more of the we need time to go do it, or if someone else wants to offer the time, great. So right now in the Accord library itself, there is all these testing functions that I showed right now. And there's not an Accord release, but you can depend on Accord with submodules and you get all that. So it would be nice to have a publish artifact so you can use everything without Cassandra. That's something that we are all willing to do. It's just, we need to do it.
So it's really valuable to write good tests and have the project happen in tree. You ever write a test that finds a problem that can't reasonably be fixed right away, but you still want to check it in? How do you balance not breaking the build with adding value tests to just do it?
Okay, that was a very good question. So the question is, there's a lot of value in writing good tests, but when you find a test where there's failures and they're not easy to fix, or they would take too long to fix, adding them in. And I think it's a case-by-case thing. In the project, our stance is no test should be failing, which means I can't add tests showing that UDTs are broken and that vectors are broken. And I make Cassandra, so I define everything as broken. When there's a small edge case in the corner that's broken, everything is fine. You can use it. So I think that there is value, but what ends up happening is, oh, there are 2 failing tests. My code didn't break anything. There are now 3 failing tests. Oh, these are all like known things. I can inherit that. And we just add more and more broken tests because we're not good at triaging. And so from that point of view, you kind of don't want to have failing tests in the project. But there's one test I did not show, and I didn't think about it until you brought this up. Disk corruption. Yay. There's only one file in SS table that is able to be resilient to it. And with BTI, we didn't solve that problem. So on the data file is able to handle corruption, and every other file is fair game, and I can show you how to corrupt every file and return arbitrary bad data. And we should fix that. But that's a very complicated solve. We have to fix that in big. So I have a test that shows that if you corrupt the index.db file, you can now start returning that the data doesn't exist, or you start returning the wrong partition. And then we don't fall back properly. And in BTI, we have the exact same problem. But it's a little bit harder because of the tree nature, so you can then just like crash in the middle. So there's a lot of value, and we just need to go fix those issues. But if you start merging them, then more things start to break, and we start making the system more unhealthy. So it's a trade-off. You in the back? You have the
I apologize if it's already explained before, but when I heard your explanation, it sounds really like module checking technique, where you like permute all events and faults coming to your system in orderly way. So my question is how you solve the state explosion problem. Do you employ like state reductions during explanations?
So the question is, there's a lot of potential states, and it will effectively take the entire end of the universe to reach all the states. So do we have any way of shrinking the states that we search to be more efficient? In short, no, we do not. That's something that Alex has talked about a lot. And when he speaks, I'm just like, I don't know what you're saying. You're too smart for me. So I'm a little too dumb for that. So talk with Alex in the corner about that. Some things you can do if you are aware of it, like I mentioned with biases before, large domains, you can start adding biases into your generators to say that like, here's a subset of the values, here's another subset of values, which one am I selecting from? So you can start doing stuff like that. But no, we don't have any shrinking ability right now. That could be a really nice thing. But as asked before, I think with Cassandra, we're still a little new with property testing. So shrinking hasn't been too big of an issue yet because we find too many faults, so we have to fix those issues. So I do think within hopefully the next year, that shrinking would then be something that we really want to care about. There's all these randomized cases that we've already tested. Let's stop testing that again and try something new. So that would be a fun place to look at. All right. In the back first, then Archie.
What portion of the test you is non-perfect? Do you think it's a good balance?
The question is, what percentage of the tests are property-based versus not property-based? Cassandra is very old, and property testing is very new, so it's a very small percentage. There's a lot of tests that can easily be replaced with a property test, and like in the CQL3 package, for example, we're going to have, here's the test for list, where we do everything we remember to do with list. Then we're going to do that for map, and then we're going to do that for set. And those get replaced by one test. So I think there's a lot of value in moving more towards doing the property test rather than, but we have a lot of tests, we have a lot of regressions that we know about that we want to make sure they don't come back. So it's a relatively small percentage, but it is growing.
Most new tests are property-based, and like many people start picking up, and so new features are overwhelmingly coming with the vast majority of their code as property-based from ground up, thanks to David.
Good.
Yeah, and if you can hear in the back or for the camera, new tests are starting to use more and more property-based testing. So we're growing better as a project. Still work. Archie?
Simulation example, you showed the components of the cluster that it's using. Are those falling into actual Cassandra components, or is it like an interpretation or model of that component?
Are you talking about the cluster class?
Yeah, cluster, and if you say you want to pick a specific part of the cluster that you want to test in the simulation, is that like an interpretation or model of that, or is it the actual Cassandra component that you're testing? If it's the latter, then how do you make sure that it's the same character?
So I said before that with the simulator, we made it so low-level things like threading, time, and messaging interfaces. So the cluster class I showed earlier is just calling simulated versions of those existing interfaces. Those are Cassandra specific interfaces, but the concept itself is portable. So rather than doing executors dot and creating an executor, we do executor factory dot what do I want as my property for an executor, and then there we're able to add our own simulation. Yeah. And I think we're done. Thank you so much, everyone.